Welcome, ladies and gentlemen, to this video lecture. So now we will look at infinite limits at infinity. So either plus or minus infinity. So for example, just think of the function that sends x to x squared. So it is a parabola, so as x tends to infinity, x squared is also going to tend to infinity. So now what we want to do is we want to rigorously define what we mean by infinite limits at infinity. So before we give the rigorous definition, let us just give an intuitive reasoning behind it. So we want to say that as x tends to infinity, our the values, for example, x squared, if we're considering the function that sends x to x squared, the values tend to infinity. So what are we going to do? We are going to say for every large number e, there exists some number m, so that everywhere beyond this m, all the function values lie above e or are bigger than e. Capital E. That is the idea. Okay, so let us use that idea to write down the rigorous definition of limits, infinite limits at infinity. Okay, definition. Let f be some function from a to infinity, mapping into the real numbers, and we've got a is of course some real number. Then by the following, so by this, so the limit as x tends to plus infinity of f of x is equal to plus infinity. Let me fix that. By this we mean the following. So for every e, every positive number e, there exists an m positive, so that if x is bigger than m, then f of x is bigger than e. Okay, and here we have defined what we mean by this expression. The limit as x tends to plus infinity of f of x is equal to plus infinity. So of course we have a version for limits that tend to negative infinity. So for example, if we've got the function that sends x to minus x squared, what does that graph look like? So as x tends to plus infinity, x squared tends to minus infinity. And now you can see here what will the corresponding definition be. So for any negative number e, we should be able to find some number m, so that beyond that m, all our function values are going to be less than this e. So that is the idea. So let's write down the definition. So by the limit as x tends to plus infinity of f of x is equal to minus infinity, we mean that for every e, now negative, there exists an m positive, So that if x is bigger than m, then f of x is less than e. And there's the definition of a limit as x tends to plus infinity, that limit tending to minus infinity. And now as an exercise, what you can do, write the corresponding limits that tend to minus infinity. So the definitions of x tends to, the limit as x tends to minus infinity of f of x. Actually, f is not defined. Let's define some function g defined on an open interval like so, and the limit as x tends to minus infinity is equal to plus infinity, and the limit as x tends to minus infinity of g of x is equal to minus infinity. So you can try and write those out and see if you get them right. Okay. So we have also seen previously that we can rework limits that tend to infinity into, or let's say limits that tend to minus infinity, we can rework to limits that tend to plus infinity. Limits by, or let's say by manipulating the functions that we are working with. And this is the theme of the next theorem. So let's consider this theorem. So we've got some function f defined on the real numbers. Then the following are true. So the following are true. So number one, if, or the limit x tends to plus infinity of f of x is equal to minus infinity. This is true if and only if. So here we see those words again, if and only if. So these two statements are logically equivalent. So this one is logically equivalent to the following. X as x tends to the limit as x tends to plus infinity of minus f of x is equal to plus infinity. So this statement is equivalent to this statement, and you can think intuitively why that is true. So if the limit as x tends to plus infinity is minus infinity, if we look at minus x, what is that? That is essentially flipping or reflecting our function f around the x-axis. So if our function goes to minus infinity as x tends to plus infinity, minus f is of course going to go to plus infinity. And the proof of this statement is not particularly difficult. You can do that as an exercise. Then number two, something similar, the limit as x tends to minus infinity of f of x is equal to minus infinity if and only if and only if the limit as x tends to minus infinity of minus f of x is equal to plus infinity. So you can intuitively see how that works. If now x is going to is going to negative infinity if our function tends to negative infinity. If we reflect it around the x-axis, then we see our function, or minus f, will go to plus infinity. So if this is f minus f, the limit will go to plus infinity. And again, the proof is not particularly difficult. You can do that as an exercise. And we can also flip around the y-axis. So if we've got the limit as x tends to minus infinity of f of x is equal to plus infinity, that is true if and only if the limit as x tends to plus infinity of f of minus x is equal to plus infinity. So you can think of how this works. If we are looking at the limit as x tends to minus infinity and f of x goes to something like that, goes to plus infinity. Now if we flip around the y-axis, if we reflect around the y-axis, this is what this is doing. F of minus whatever we put in there. So if this is the graph of f of x, f of minus x goes to plus infinity as x tends to plus infinity. So this transformation has the effect of flipping around the y-axis. Okay, so in this way, what is this theorem telling us? In this way, we can rework any of these limits that tend to plus or minus infinity into limits that tend to plus infinity or as x tends to plus infinity, our function tends to plus infinity. But just by reflecting the functions that we're working on, that we're working with. Okay. I will end the video here. In the next one, we will do some examples. I will see you in the next one.